Right. Good day, everyone. Good morning. Good morning. How are you?
We are good, sir. And you?
I am fine. I'm fine. I hope everything is okay. Yesterday we finished atoms. Right. We started matter and finished atoms. And then we're continuing with matter, but we're gonna start with a different section, electrostatics. I'm gonna introduce you to electrostatics. And then on this introduction, I'm going to need you to actually pay attention because there's a bit of mathematics involved and a little bit of more science involved. Because you guys told me that you find out that some of the grade 8 or 9 that you teach, they tend to have more data than you have actually covered here. So I'm going to have to push, but at the same time, I'm going to have to remember that this is not, I'm not supposed to go too deep. Right. So now here goes. So welcome today everyone, and to those who are just entering, good morning. And then welcome to the electrostatics section. So what is electrostatics, guys? This relates to the stationary charges of fields as opposed to electric current. Right. What do you think that means? In your own words, what do you think electrostatics is? Anyone? Anyone, guys? What do you think electrostatics is? The comrades are quiet. What do you think electrostatics is? Anything that you think no one wants to answer today. You see that thing that happens when you take off your woolen jersey or something and it says, that's electrostatics. Before I assume that the comrades that don't want to answer today, can you hear me?
Yes, we can.
Lovely, wonderful. So electrostatics means that electricity which is generated by the rubbing of wool, the rubbing of hands, contact. Have you ever realized that sometimes when you're standing next to another person and you try to rub when you're passing through them, it just is, that's electrostatics, right? So that's a force between charges or a force that comes out between electric fields, right? That's what electrostatics is all about, right? It relates to stationary charges. By stationary charges, we mean a charge that is not moving. You see electricity in a wire, it's movement of electrons, right, due to an electric field. But when we're talking about electrostatics, we're talking about charge which is generated by rubbing. You know how this happens. When, for example, Sibanda here, right? Sibanda here suddenly rubs his hands too much here. You know what happens here? If he puts a piece of paper inside in the center of his hands there, and then he starts rubbing vigorously, rubs. Then after rubbing, what happens is you generate heat. Once you generate heat, then the atoms that we're talking about yesterday, they tend to move faster, they gain speed. When they gain speed, that's when now, which means there's displacement of electrons. Electrons start to separate. You know, when you shake things, you shake atoms, the particles inside, they start moving faster. When they start moving faster, that means electrons there break free. They break free. Once they break free there you've created a charge. But look at what's happening. You're stationary, you're in one place. Only you is rubbing the piece of paper, right? So when you rub a piece of paper until the atoms get hot and then they gain speed in the particles that they have, electrons break free. Once they break free, then you've created a charge. When you touch another material which has been rubbed like that or which has been rubbing, that's when you hear, right, a spark. That's electrostatics, right? Now, so This can be done by force between two charges or electric fields which have been made. For example, sometimes you may find out that you are electrically charged on your own. You've been walking, when you're walking on your own, you keep swerving your hands and your jacket keeps saying, something like that. Thereby, you're generating a stationary charge. And then when you meet another Sivanda there who has been doing the same thing, you guys touch or pass through near each other in such a way that the electric field becomes too much. You hear, that's electrostatics. So now here are the charging methods. As I was saying, there's friction, right? Let's annotate friction. That's the one that we've been talking about. When Sibanda rubs his hands just like that, that's friction, right? In contact, Sibanda is charged and Sibanda meets Tsebelishe, and then they rub hands there. It happens again. And then there is also what is called induction. This is a special one, right? Induction, there's something that is called electromagnetic induction, but we're going to get to it later. So this one is called induction. Induction is the generation of charge or electricity using what? A magnetic field and another power source. It's either we use wind, or either we use water, moving water. When moving water turns turbines around a magnetic field, they create a charge or electricity. That's what refers to induction. But this one, we're going to go to it. It has its own topic called electromagnetic induction. Right. Anyways, to continue, an object becomes charged when it gains or loses electrons. Right. Listen to this statement. An object becomes charged when it gains or loses electrons. Right. That's what I was talking about a few minutes ago when I was saying when you rub your hands together on a piece of paper or material, what happens? The particles gain energy because they start moving, they gain heat. When they gain heat, they start moving faster. When they start moving faster, electrons, they just break free. So it's either they break free or either they gain which broke free from somewhere. Right. And then once they gain or lose, there's a problem. Remember, we said an atom must have equal positive charges in the center, like the electrons on the outside, such that it is balanced. That's what we said yesterday. We said an atom has a positive charge in the nucleus, right? And there's electrons on the outside. And then we said the number of protons inside and the number of electrons inside, they are equal. Hence, it is a neutral charge. But once it gets heat and gains energy and loses an electron, which means now there are more protons than electrons on the outside. Since the protons are positive, they need to have a positive charge. If, however, it gains an electron from another atom, right, that means there will now be more electrons than protons, which means it will have a negative charge, right? So if an object loses electrons, it will become positively charged, more positive. So if it loses electrons, that means there's no balance. There's now more protons than electrons. If it gains electrons, it will become negatively charged. That means now there are more electrons, the negative ones, than the positive ones, which are protons, right? So that's what this statement is also trying to explain there, right? So now, here is what we call the SI unit for charge, right? You know what SI units are? SI unit is the standard units that are used all over the world. You know this thing that there's Chinese, there's Americans, there's the English, right? There's the Dutch, there's the Africans and etc. We all have different measuring instruments and different standards. But in order for all of us to know if we're working on a project that no, I'm working with someone in China and someone in UK, to keep everything together so that when you interface everything, it's interfaced very well and it works well integrated. We must all work under the same standards. That's what is called SI units. So the SI unit for charge is the coulomb. Coulomb, boys, Coulomb. English, you know, the pronunciation differs. Don't laugh sometimes. So, and it's represented by C. So, for example, when in calculations, we call charge Q. We represent charge. It's Q represents charge, right? But then the SI symbol, that is the unit, that will be Coulomb, UC, right? Remember that. Now, what's this? Just take that, right? And then let's go to the next one. Then there is something that is called the Coulomb's law, guys. This Coulomb's law, you'll find it even when you're teaching, when you go out there teaching grade 9s, 10s, I don't know. 8 maybe, but 9s, 8, 9s, if you get to teach 8, 9s, you'll meet this Coulomb's law. It's similar to another law, which is called the gravitational force law. It's also similar, it's similar to many laws. It's like this approach, these scientists were copying each other. They're just trying to show us that nature, no matter what kind of nature it is, they all behave similar. So what does Coulomb's law talk about? It talks about attraction between two things, right? And the law of attraction between two things. So what it says is the force between charges is described by Coulomb's law below, right? Let me annotate so that I talk. Coulomb's law states that the electrostatic force, right, between two charged objects is directly proportional, right? The electrostatic force, Fe underscore E there, right? Between two charged objects, these two charged objects are Q1 and Q2, right? Is directly proportional is represented by this to the product of the two charges, right? That would be Q1 by Q2, right? And inversely proportional to the square. Inversely, that means underneath. Inversely proportional to the square of the distance between their what? Centers. Inversely proportional to the square of the distance between their centers. So what is the distance between their centers, right? That will be R2 minus R1, wherever you are measuring from radius 1 to radius 2. Because that means, let me wrap it a little bit to explain to you something. Here's your raise, right? So let's erase the 2, take out a bit there, right? Then we can go back to pen. You see, let's say you have two charges, these two big charges there. This one is Q1, this one is Q2, right? And then from there, check that here, there's a distance to there, and here, there's a distance to there. Right, let's change color. So from here to there, that would be radius 1. My handwriting sucks. So from here to there, that would be R1. Change pen again. Then from here to there, that will be R2. Right. So now the distance between their centers, what is the distance between their centers? That's R1 plus R2. Am I right?
Yes, you are.
So that will be R1 plus R2. But they said to the square. So the square, this is supposed to be squared, right? So Coulomb's law states that the electrostatic force between two charged objects is directly proportional to the product of the two charges, Q1, Q2, and inversely proportional to the square of the distance between their centers, of which that distance will be R1 plus R2, right? And then they say it's square, that will be squared, right? So remember to state this in words. In a test, if they say state Coulomb's law, then you can state that in words. right? Say give Coulomb's law fully, right? You give that Coulomb's law fully in words. But if we say put a formula, I will show you the next formula because we're not done. Remember, I don't know how far your math is, but if we talk about proportionality, there's a difference between proportionality and uh, there's a difference between proportionality and the equal sign. When you're saying it's proportional like that, you represent it like this. But the moment you introduce the equal sign, there must be a constant here, right? A constant of proportionality, of which you will see when we're going to the next page. All right, let me clear that until it moves nicely. Okay. So this is what I was trying to explain on the previous page. So like charges repel, we all know this. Like charges repel and unlike charges attract. But now this is the law represented in terms of a formula, right? When you're representing it in terms of words, you put it like this. You must take note of the maths, right? Right, over r squared, right? So what this means is force, that's the force which we say Fe on our annotation so that we remember that we're talking about the electrostatic force. And then Q is charge 1 and charge 2, right? And then C, R is equal to distance in meters. Take note, SI unit is newtons, the radius is in meters, right? This R, which is represented as R squared, you remember what the formula said. It's the distance between the two centers. So that's R1 of charge 1 plus R2 of charge 2. That gives you R, right? And then this K is what I was talking about, which is the constant of proportionality. Here it's called the Coulomb's constant, which is this value. 9 by 10 to the power 9 Newton meter squared per Coulomb squared, right? So take note of the SI units. Right? Take note of the SI units. This one we told you that it's C, the Coulomb, right? So you see now, there's a difference between representing a formula in English by stating and mathematically. And now you understand what this means. R1 plus R2, blah, 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 what Q1 or Q2 and K means, and what F will be and R squared. Right. Any problems with this formula?
Oh, sir.
No, 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 no.
So far, so good. All right. Okay. Let's do it this way. Now we come to what is called electric fields. What is called electric fields? An electric field is an area where a charged object will experience an electrostatic force. Now, I want you to understand this one clearly now. You must, when we're talking about these things, one thing that I want you to understand is that there is no useless topic here. Just check from the moment that we started, those things are following each other. The one that was previously done on the last day or last week, it still matters on the other one. It's a foundation, a building block of the other one. So now electric fields, they are built on the previous studies that we've done in class. So an electric field, right? Don't zoom. An electric field, it is right, is an area where a charged object will experience an electrostatic force. Remember, we've talked about an electrostatic force. We've talked about the charge, right? Now we're talking about an electric field. An electric field is an area where a charge let's say Q1 or Q2, will experience a force, right? Will experience an electrostatic force. So remember, we already have a force that we know, right? So which means a charge, if it's put on an electric field, it will experience a what? Force. All right. Now let me show you what they are trying to explain there. What they are trying to say with this thing. An electric field is something like this. Consider it as two barriers, which are like this, right? Two barriers. Let's put them like this. This one, ta, 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 ta. And then this one, positive, ta, 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 ta. Right. So an electric field is the region inside here, which is influenced by a positive field and the negative field. So between the positive and the negative, they experience an electric field. That's why when you put a charge here, Q1, right, its direction of movement will depend on its charge, what kind of charge it has. If it's positive, like charges repel, it will be attracted to the negative, right? If it's negatively charged, with negative and negative, it will repel. So it will be attracted to the positive barrier, right? So hence, an electric field is an area where a charged object, Q1 or Q2, this one, will experience an electrostatic force, right? So if a negative charge or a positive charge is put in a field, the field is where there are two barriers, positive and negative. It will be pulled to one side, either by the positive barrier or by the negative barrier, but depending on what? Depending on its polarity itself, right? That's what they are trying to explain with this statement right here. That's what an electric field is, right? Now, they are saying electric field lines. Electric field lines have the following properties. They are imaginary lines. Yes, that's true. Consider a battery, or consider putting like a charge in an atom. For instance, you can't even see an atom. And what I was trying to describe here, right, with this barrier, is something that you can see. You can't see, you cannot see it. But the only thing that you know is happening is when you see your TV on, your torch is turning on, or your jacket is saying, whatever is happening, which conducts electricity, or which depends on electricity. But to physically see the movement of those charges, you won't. Hence, they are saying, imagine an electric field is what is having imaginary lines. And one other most important thing that you need to know about an electric field is that its imaginary lines are like this. It flows in this direction from positive to negative. You remember a battery, how it is. It flows like that, right? Those are the imaginary lines. They are directed away from a positive charge and towards a negative charge. You see that? Never cross or touch each other. So you see what's going. They are parallel, straight from the positive side to the negative side. They are not crossing each other like this. And then you say that's an electric field. No, 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 no. This is a no, no, no. They are parallel, straight. They do not cross each other. They start and end perpendicular to the surface of each conductor. So here my drawing is terrible. That means that they are at 90 degrees. Here where they start and here where they end, the angle is 90 degrees. They are perpendicular to the surface of the charged conductor. Right. I hope this explanation is clear. Any questions on this one? Any questions, guys, there?
It's clear for me, sir.
The other comrades, they feel okay.
Yes, it's perfectly clear, sir.
Yes,
We're okay,
sir.
sir.
Yeah.
Yes, sir.
Wonderful. Wonderful. Now, see now, what I keep telling you that there is nothing that we are just doing for pleasures. These things, they are what? They are interrelated. So for now, on the first half of this semester, we're building blocks. We're just putting a foundation concrete. The real deal, the real makoya of what we're doing is gonna come. So master the building blocks so that when we reach the climax of what we're doing, you're home dry. Right. Now we enter into matter and the materials. Right. Matter and materials. What is matter, guys? I'm sure you've seen this before, maybe in primary or wherever, secondary, high school, anybody in your own words. Nobody should be shy here. You should ask questions. Comrades, I'm talking to you. The comrades today, yes, anyone.
Sir. Yes, with my understanding is that matter is anything that has mass.
That is mass. Okay, you're also right in a way. Anyone else?
Sir,
Yes.
yes, I think when we are talking about matter, we are talking about anything that you can see physically. That is why they are saying it can occupy a space and it has a mass, you can weigh it.
Yes, yes, that's also true. Qiniso Mbonambi, I see a hand, you can speak. Qiniso. Now, maybe
I'm here, Mr.
Yo, I'm saying I'm seeing your hand, you can speak.
Yes, Mr. It's not Penis on Bonamba. Unfortunately, I've used his laptop, so I'm small my flag.
Oh, okay, okay.
Yes, Mr. I think when you speak of matter, it is anything that has a space and it has a density. Is you can see it, and sometimes you cannot see it. Like a gas, you cannot see a gas. You cannot see a gas, but it has a density. That's what I'm trying to explain.
That's also true anyway, you're right.
Yeah, thank you very much, Mr.
Okay, anybody else? All right, let's see what they're saying. They're saying matter is anything that occupies space, has a mass. All right, gas is matter, air is matter, anything is matter. That's what they are trying to say. Matter exists in different forms. All right, in different forms, either as a solid, liquid, gas, or plasma. Right. You know what solids are, right? Solids are blocks, something which is hard, wood, brick, block, metal, right? Liquid, they're talking about things like water, paraffin, all those things, petrol, whatsoever, oil, crude oil, what. Gas, they're talking about oxygen, carbon dioxide, methane, etc. Right. Plasma now, that's the important part. What do you think plasma is? In your own words, anybody to explain to the class, you can find out that there's someone who doesn't understand what plasma is. Anybody, guys, to tell us what plasma is? You guys are quiet. Yeah, you guys, yeah, you surprise me. Some of you in the past 2 years or past 3 or 4 years back there, I'm sure at your homes there were these big plasma televisions there that you're watching TV on. And you say at home we got a plasma, we got the cinematic 4K TV, what's so on and etc. What's a plasma then? A plasma is liquid crystal display. So what happens? What's happening with plasma? It's something which is in between liquids, right, and crystals, right? It's a form which is in between being a liquid and a crystal. So in other words, it's the form which is between a solid, liquid, gas. It's in between. It doesn't exist as one thing. It's in all forms, right? Guys, can you hear me? Someone is crying about not hearing me.
Yes, we can hear you, sir.
Okay, so that person is a problem. Right. So a plasma, it's something that, guys, is in between all these states. If you just open your Google and check whatsoever, you will find the real definition of plasma. Plasma is a light yellow liquid in the blood that carries water, salt, and enzymes. That's for the blood, right? That doesn't mean it's solid. No, it's still carrying what? Food, salt, and some enzymes, which means it has solids inside. At the same time, it has absorbed oxygen inside it. It has gas in it, right? So it's something which is in between all states, right? That's what you must think about. So there are different types of materials that are made up of matter. And we have said that matter is either solid, liquid, gas, and plasma. Now we'll go on to further classifications. All right. So what are materials? These are things needed for an activity, e.g. building materials, and these different materials of different properties and different uses. These materials exist in nature as raw materials. This is what I really don't like, guys. I really don't like this. That's why when I set these meetings, I set them to in a way that when someone enters, they are on mute. Every family fights, but it should fight with respect. It's getting out of hand now that every time these days we are busy talking, there's someone who's negligent. They forget that they must mute themselves. And to be quite frank and honest and strict, it's very annoying, right? Let's please respect each other as a family. Think about the other guys who are quiet and they're on mute. We are not interested in your third party business on the others. I hope that is clear. So to continue there, guys, let's check what the other two people said here on chat so that we don't they're okay. They were talking about that they can hear us. Right. So we can continue. We're saying that materials that exist in nature, for example, the other different types, they are raw materials, e.g. coal, wood, air, and water. Basically, these from what we've been watching on TV. Haven't you ever seen those cartoons like the Airbender, the movie called the Airbender? There's earth, wind, and fire, etc. Those are some of the things that exist in nature as raw materials, right? Then some materials may be manufactured or processed, e.g. clothes, that's processing and manufacturing. Furniture, that's processing wood into a different kind of thing. Cardboard, that's another processing because you're manipulating wood and turning it into paper. Plastic, manufacturing. Materials may be organic or inorganic, right? I hope people know how to differentiate between organic and inorganic. Organic materials are made from living organisms, e.g. they contain carbon, right? And then inorganic materials are not made of living organisms. They contain metal atoms or elements, as we talked about 2 days or 1 day ago, things like calcium, helium, whatever. It will now be a combination of those things That's what we call inorganic materials. Right. So key aspects of material research, the most ones that are always everywhere. Remember what we said, they consist of raw materials, organic and inorganic. So it's quite a mixture there. Right, there's mild steel, there's copper, there's etc. Right, let me annotate. You see, there's ferrous. Ferrous means iron. Remember that. Ferrous is things that contain iron. Non-ferrous, those that do not have iron. Right. Mahogany, these are natural ones now. They are coming from what? They give us pine, mahogany, oak. You know, all those mahogany tables and etc. Those ones that when you find in nice places and stuff like that. And then these plastics, these ones are from manufacturing, these ones, inorganic. And then there's the environment, non-toxic and toxic. So this is the center of what materials are. So you can erase everything and then annotate here that, look, the mother of all things there is the word materials. And then they split each other into what? Environment, ferrous. You see now, I'm really quite getting annoyed. Badowski. So see what it does. It actually quite takes my mind off on what I've been talking about. Anyways, sorry about that, guys. Let's talk about the particle theory of matter. I'm sure you guys have met this one before. I'm quite sure you've met this one before. Particle theory of matter. What does it say? The particles of matter are in a constant state of motion. That's what I was trying to say in the beginning today when I was talking about electrostatic charge. And I was saying that the movement there will cause atoms to move faster, gain more speed.
Hey. Iphathe imoto phi?
Who's Tubeli's friend, if we may ask? Tubeli, can you hear us?
Yes.
I'm getting quite annoyed. Please, can you mute yourself and respect some of us? I've been saying this before, but you keep unmuting yourself, and I've stopped lecturing again because of the noise from your side.
I'm sorry, sir.
All right, thanks. So the particles of matter are in a constant state of motion. They have kinetic energy. So that means, guys, that these particles are always moving, right? For instance, if you want to see that particles are always moving, let's take clear water, right, and introduce dye into it, right? You will see that the dye is moving, but that one is another kind of law. But to show you that it's always moving, if you find dirty water or something there, look at it, you'll find that the particles are moving up and down and stuff like that. So the particles of matter are in constant motion. They have kinetic energy, right? The energy of movement, kinetic energy. What you must also understand as point number 2 is that there are spaces between the particles of matter, right? So we say point 1, the particles of matter are in constant motion. Point 2, there are spaces between the particles of matter, all right? Point 3, the particles of matter can attract or repel each other, right? So this is the particle theory of matter. It's stating 3 points in one go. The particles of matter in constant state of motion, that is, they have kinetic energy. Number 2, there are spaces between the particles of matter. Number 3, particles of matter can attract or repel each other. All right. But now we're going to go in detail by different types of matter, explaining where the spaces are, where kinetic energy is more, where they attract or repel each other. Right. So from what you can see now, down shown below, here is the solids. Here is the liquids. Here it's the gases. Without going to the next page or going to the note, you can actually see the gases take any form of shape that they are introduced to. The liquids just contain or take the lower shape of where the gravity pulls them to. Only the solids are stubborn. They try to maintain their shape. They are stubborn to a certain extent until heated. So you can always see immediately that the gases have more space between their particles. More space. Liquids also have space, but their spaces are less than those in gases. Solids have space, but their spaces are the least of all the other spaces of the other particles. Right. Let's clear that and take go to the next page. So now we start with solids. Here shown is the model of a solid. Right. In a solid, the particles are close together. Right. Very, very close, as I was showing you. They have strong bonds. So take note of these points. The particles are close together. The particles they have strong bonds in between. Particles is not free to move around. So you see solids do not take any shape. They are not easily bended. That means these particles are what? Are not free to move. They are bound, right? They have very low kinetic energy. They only vibrate. And as you all know, it's very, very hard to compress a solid. They cannot be compressed as air spaces between particles are limited, e.g., ice or bricks, etc., those kinds of solid. Right. Now we come to the model of a liquid. As I was saying, particles move around more freely than those of a solid. There are more spaces in liquids than there are in what? In solid. That means that they can slide over each other more easily. Right. Hence, that these particles have more kinetic energy. Yes, because they move more than those of solids. Right. That means they have more kinetic energy. The liquids do not have definite shapes. They take the shape of a container. That's one of the things that I was saying. Even if this glass, even if it was shaped like this, like that, they would first fill in this shape, which is funny here. Right. But if you try to put a solid there in a container, it will come here and not fit and stop there. Right. Take note of that. So liquids do not have definite shapes. They take the shape of the container. There are larger spaces between liquid particles that we've seen even before. All right. With that in mind, guys, we have run out of time. It's now 10:23. I have to prepare for my other lecture in 7 minutes. So I will stop here today and I will say thank you very much. I was enjoying some of the replies that were coming from the comrades. I hope we continue talking nicely and enjoying like this. Otherwise, have a great day today, guys. I will see you tomorrow. If there are a few questions, but in the meantime, you can, feel free to move on to other things for now. Bye-bye.
Sale kakuhle Themba.
Re leboga o tsamaye sentle mister.
Leboga ntate, o tsamaye hantle le wena. Ngiyabonga nduna.
Le nna ke a leboga.
Danke
Hayi
ntate.
wayongathethi isiXhosa wathetha ntoni wayongathethi isiXhosa.
Awangisazi nje mfundini.
Hayi uthetha nesixhosa kaloku.
Siqhela kaloku.
Uqhemile kaloku wena.
Akukho nto ichenyiweyo makuthethwe isiXhosa babhema
Hlangana namaXhosa nisiyeke nje.
Bafowethu, at least asikhulumeni
Anisiyeke
isiNgisi.
ngamaxhuku.
isisulu
Anisiyeke
sakhe
ngamaxhuku, amaXhosa.